This is section 2.5, and we are still working with exact equations. So we remember this is our form that we look for exact equations. But we're going to start with an example where it's not exact. So if this equation is not exact, but the equation where you multiply through by some function mu is exact, then we say that the function mu is an integrating factor of the original equation. So we're going to show how that works with an example. So we're going to show that 1 over 3x squared plus y squared plus 2 times dx plus plus xy plus y cubed over 3x plus 2 times y over x dy is equal to 0. We're going to show that that is not exact, but if we multiply by mu equals x, x will be an integrating factor, so that will be exact. So let's write down some information that will be important. M in this instance is 1 over 3 x squared plus y squared plus 2, and n is equal to xy plus y cubed over 3x plus 2 times y over x. So we want to first show that the equation is not exact. So in determining if something is exact, we're looking for delta m delta y is equal to delta n delta x. So if we want it to not be exact, we're hoping that these will be not equal. Let's start with delta m delta y. So what is the partial derivative of m with respect to y? Well, since we're only taking derivative with respect to y, these terms that don't have y's in them get to act like constants, so they just fall off. So all that's left is this y squared, and the derivative of y squared with respect to y is 2y. Now for n delta x, all of these terms have an x in it, so there's going to be a lot more pieces here. We can tell immediately it's not going to be 2y. The derivative of x times y is y with respect to x. But then we get into all these x to the negative 1 values. So remember, the y cubed over 3 is just a factor in this instance. But the x to the negative 1 here is going to become x to the negative 2. And then we carry that negative 1 out front. Remember your power rule. So you'll see how we get these pieces, and these are clearly not equal. 2y is not equal to y minus y cubed over 3x to the negative 2 minus 2yx to the negative 2. So they're not equal. That's the first step. Now we need to show that the integrating factor is going to make them equal. So we're going to multiply through the entire equation by our integrating factor x. We say mu of xy is equal to x because it's possible that mu would be a multivariable function. But in this instance, it's just in terms of x. So here we're multiplying through by x, and then we simplify, carrying the x through the brackets. So now we have a new m and n value, and delta m, delta y, well, that's the derivative with respect to y of 1 over 3 x cubed plus xy squared plus 2x. Well, that has no y term, that has no y term. So all that's left is the xy squared. So we get 2xy. The 2 comes out front as a factor. Now we're going to compare that to delta n delta x, which is the derivative with respect to x of our n term, which you can see right here is x squared y plus y cubed over 3 plus 2y. Well, the derivative with respect to x, that has no x's in it, that has no x's in it. All that's left is this x squared y, which will become 2xy. So these two are equal. So yes, we are exact now. So mu is an integrating factor. Now, here's an important note. One should always check that results determined this way are also results of the original equation. For instance, since our integrating factor was x, we multiplied the equation through by x. There are no longer any x terms in the denominators. So it may appear that x equal to 0 may be a solution, but we know that x equals 0 is not a solution to the original equation because there were these x's in the denominators. The function would never even exist. Okay, but now we're just going to move on as we would have in the last section. We have a new m value, a new n value, now that we've multiplied through by mu. And we're going to evaluate using our previous steps. So we have these old rules from the last section that are going to be very useful. Delta f delta x is equal to m, and delta f delta y is equal to n. So we're going to make use of those one at a time. So we'll start with delta f delta x is equal to m, and then we will integrate both sides with respect to x. So that's how we isolate the f term. And now on the right, we have the integral of this m function with respect to x, plus, if you recall, it's not just a plus c value, it's actually any function of y. And the reason for that is we're integrating with respect to x. And when you integrate with respect to x, that means every other variable needs to act as a constant. So since we are also dealing with y, this constant is not just some number, but rather any function of y. Now we substitute in our m value, which we know. We'll just scroll back up to show that. M is this right here, 1 over 3x cubed plus xy squared plus 2x. And now we're going to integrate that with respect to x. So power rule says raise this power by 1 and then divide by the new power. So we get 1 over 12x to the 4. We do the same with all of the x terms. And g of y is our c value, our constant. Now, we've made use of delta f delta x. We have an equation that f is equal to. But the problem is it's not very exact because we don't know what g of y is. So that's our last problem, solve what is g of y. So we can figure out exactly what f is equal to. This is where we're going to make use of our second fact that delta f delta y is equal to n. So let's take the derivative of both sides of this equation with respect to y. So we get delta f delta y on the left, and on the right we have the derivative with respect to y of all this. We say partial derivative because it's a multivariable function. There's x's and there are y's. Now, n is what delta f delta y is equal to from here. And on the right side of the equation, we're just going to take the derivative with respect to y. But note that not all these terms even have y's in them. So this 1 over 12x to the 4, that's just a constant. X squared, that's just a constant. Here we actually have something. We're going to take this 2 and bring it out front as a factor and reduce the power. So we get x squared y plus whatever the derivative of g of y is. So we get g prime of y. Now we finally plug in what n is equal to. So if we scroll up, we see our n equation. N is equal to x squared y plus y cubed over 3 plus 2y. So we perform that substitution for n. And now we're going to cancel out any common terms. We have an x squared y on both sides, so we can get rid of those. And remember, we're trying to solve for what g is, so we can actually get a formula for f. So we have the g prime of y is equal to y cubed over 3 plus 2y. Well, we want to know what g is, not g prime, so we need to integrate both sides of this equation. And this isn't, luckily for us, this is not a very difficult integration. We just use our power rule twice. And we get the g of y is equal to y to the 4 over 12 plus y squared. Now we're going to take that, plug it back in for g, and we're going to get our final answer for f, that the multivariable function f of xy is equal to 1 over 12x to the 4 plus 1/2 x squared y squared plus x squared plus our g value, which is 1 over 12y to the 4 plus y squared. And that means that all of that equal to C is a solution, where C is a constant. Now, in this example, we were provided with the integrating factor. Now we're going to determine how we can find such an integrating factor. By our test for exactness, we know that, remember, our new m value is mu times n, and our new n value is mu times n. So this must be true. The derivative of mu m with respect to y must be equal to the derivative of mu n with respect to x. We're going to use our product rule on this, because remember, the derivative of mu m is the derivative of a product of functions, mu times m. So that gives us mu times the derivative of m plus m times the derivative of mu. And then we do the same thing to the right side with n. That's just our product rule. Now we move the mu pieces to the right. Now this may be very difficult to solve if mu is a multivariable function. However, if we get to suppose that mu is either a function of x or y instead of both, that's very powerful. As we see here, we would be able to plug in that the derivative of mu with respect to y is equal to 0 if x was just a function of x. Sorry, if mu was just a function of x. If we were able to do so, then we would actually be able to find a value for the derivative of mu with respect to x. Now we would be able to do a very similar thing if we instead suppose that mu was a function of y. We would get that the derivative of mu with respect to y is equal to this expression here. Mu times the derivative of n with respect to x minus the derivative of m with respect to y, all divided by m. Now, if it so happens that this is a function that depends only on x, then this rather difficult looking equation actually ends up being separable. Now, how would we accomplish that? We would want to get all of our mu's on the left and all of our x's on the right. So we have our 1 over mu delta mu. And on the right, we have all these x and y functions, but we're only taking the derivative with respect to x. So now we're going to integrate both sides. Sorry, we're integrating with respect to x on the right. So we integrate both sides, and the left side's simple enough, that just becomes ln of u. The integral on the right side, we don't have enough information to simplify that yet. We don't know what the derivative of m with respect to y is, what the derivative of n with respect to x is. But we know from our assumption, I'm going to scroll back up here. I may have said that it's a multivariable function, but we are supposing that it depends only on x. So that's why it makes sense to us to integrate with respect to x here. So we get that by raising both sides as powers of e, we actually have a value for mu right now, as ugly as it may look. Mu is equal to e to the power of the integral of the partial derivative of m with respect to y minus the partial derivative of n with respect to x, all divided by n. Now, that's if we suppose that mu is a function of x. Alternatively, we could suppose that mu is just a function of y. And we reach the same value with these two just flipped and m on the bottom instead of n. One thing I'll point out, this exp, in case you're unfamiliar, means e to the power of. In instances where the type would get too small, I'll sometimes change to exp, but these two mean the same thing. Okay, we're going to use all that new knowledge for our example here. We're going to solve xy plus x times dx minus 1/2 x squared y plus ln y dy is equal to 0. Step 1, we're going to go through pretty much every section we've done up to this point to see how on earth are we going to integrate this thing. So step one, is it separable? And without much work, we can clearly see that there is no way we are going to get all the x terms with dx on one side and all the y terms with dy on the other side. So no, this is not separable. Next, is it linear? That would be section 2.3 where we learned about that. Problem is no, it's not linear, and that's because of this ln y term. Remember that in a linear equation, we needed the y term to be by itself, multiplied by some function of x, certainly not inside of a ln function. So no, we fail on linear as well. Is it exact? Well, for exact, you're going to compare the partial derivative of m with respect to y to the partial derivative of n with respect to x. They're close, but they're not equal. So we get that step 3 fails as well. They're not exact. Go to step 4. This is a new one for us. Could a potential integrating factor mu be a function of only x? Well, we look at this function that we were just solved for, and we're going to plug in our known delta m delta y, which is just x. It's right here. And then we subtract our delta n delta x. So that's this function here. And we divide by n. Again, without much effort, we can see that there are y terms in there, and no amount of simplification is going to get rid of these y terms. That ln y in the denominator is not going anywhere. They're not going to cancel out. So we failed on step 4. Mu is not a function of only x. Could mu be a function of only y? Well, we would look at our y expression that we measure. So that's delta n delta x minus delta m delta y divided by m. Well, we know delta n delta x and delta m delta y. They're the same things they were up here. They're just flipped around this time. So we get negative xy minus x. M is xy plus x. This does actually simplify. There's a common x term that's going to cancel out everywhere. And then we can factor out a -1. And we get that the answer is just equal to -1. And remember, a constant is vacuously true. It's arbitrarily a function of y. So yes, mu is an integrating factor, and it's a function of only y. Now, remember that mu is not just equal to -1. Mu is not equal to this. Mu is equal to e to the power of the integral of that. So that's what we get. Mu is equal to e to the power of the integral of -1 with respect to y. That's simple enough. That's equal to -y. You could put a plus c in, but we're going to skip that part because it would cancel out. So we are just content with -y there. So we take our function, our m dx plus n dy is equal to 0, and we multiply it through by this new integrating factor, mu, which is equal to e to the -y. And then we simplify. Here, we're just going to check that it is exact. So if we take the derivative of m with respect to y, we get -xy e to the -y. There's a product rule involved in there, but nothing too difficult. We're going to compare that to delta n delta x, and they are equal to the same thing, -xy e to the -y. So yes, this is exact because they are equal. So now we can finally do things as we would have in the last section. We're going to calculate f of xy. So remember, we have our two equations. Delta f delta x is equal to m, and delta f delta y is equal to n. So we'll start with this one, and we'll integrate both sides with respect to x. Remember, our constant is any function of y. We're going to plug in what m is known to equal, and then we're going to integrate it with respect to x. Now, when we integrate it with respect to x, we get to act like all of these terms that only have y's in them, that's just constants. So all we're really doing is increasing this power of x by 1 and then dividing by that number. So this is what f is equal to. This is what we're looking for, but we have this g of y we don't know yet. So now we need to solve for g of y. And to do that, we're going to use our second bit of knowledge we know about f, that its partial derivative with respect to y is equal to n. So moving on, we're going to take the derivative of both sides with respect to y. So this is the derivative of what we just solved for with respect to y. Note how gy becomes g prime of y. And when we take the derivative of both sides with respect to y, this 1/2 x squared, we've just factored that out. Don't need to worry about that. It's a constant. But this e to the negative y times y plus 1, that is a product rule. So we get a couple different pieces added together there. And then we simplify. Simplify again. And then we plug in what n is actually equal to. Well, after we multiplied n by mu, it now looks like this. And now we're going to cancel out whatever terms we can find to cancel out. So this negative 1/2 x squared y e to the negative y, there's actually one of those on both sides, so they cancel out. And we're left with negative e to the negative y ln y is equal to g prime of y. Now, sadly, this is not an integral that is easy to calculate. This exercise was mostly about learning all the steps involved, so we will forgo the final integration and be satisfied with this answer, that f of xy is equal to 1/2 x squared e to the negative y times y plus 1 plus g of y. Equivalently, that would be equal to f of xy is equal to 1/2 x squared e to the negative y times y plus 1 plus the integral of negative e to the negative y times ln y with respect to y. So remember, normally, and certainly on any exam, I will give you something that is actually solvable. But sadly, at the end of this example, we reached an integral that is not solvable, not easy to calculate. And then finally, we set it equal to c, where c is some constant.